now we have this proposition. Mutually orthogonal non-zero vectors are linearly independent. Let's see how we can use this in an algorithm. What happens when we call the orthogonalized procedure on a list, vlist, consisting of the vectors v0 to vn, when those vectors are not necessarily linearly dependent? So let's imagine that the dimension of the span of these vectors is less than the number of vectors. We run orthogonalize on the list of the vectors, and it returns some output list v0 star through vn star. Now, we know that those vectors in the output are mutually orthogonal. They can't be linearly independent because they span a space of dimension less than their number. It must be that some of them must be 0. Let's consider these vectors, but leave out the 0 vectors. That doesn't change the space spanned by them. So let S be the subset of the output vectors, v0 star through vn star, consisting just of the non-zero vectors. Well, the span of S is equal to the span of all the vectors, v0 star through vn star, because 0 vectors don't contribute anything to the span. This is equal to the span of the original vectors, v0 through vn. That's the correctness property of orthogonalize. And the proposition implies that this set S is linearly independent. So we've got a set of vectors that are linearly independent and span the same space as v0 through vn. So S is a basis for that vector space. So in principle, this algorithm should find a basis for the space spanned by the input vectors v0 through vn. First computes v0 star through vn star by running orthogonalize on the input vectors v0 through vn. And then it returns the lists consisting of those starred vectors that are non-zero. For example, suppose we run orthogonalize on the vectors v0 through v6, and it returns the vectors v0 star through v6 star. And suppose from among these output vectors, v2 star, v4 star, and v5 star are 0. In that case, the remaining output vectors, v0 star, v1 star, v3 star, and v6 star, form a basis for the span of those initial input vectors. Now, you might remember we had a lemma that said that every finite set T of vectors contains a subset that's a basis for a span of T. Can we adapt this algorithm to give us such a subset basis? So given vectors v0 through vn, find a subset of these input vectors that is a basis for their span. Here's the proposed algorithm. We run orthogonalize on the list of input vectors v0 through vn, getting vectors v0 star through vn star. Now, we return the list consisting of those original vectors that correspond to starred vectors that are non-zero. Does this algorithm work? I'll illustrate by example that the algorithm is correct. Well, let's say we ran orthogonalize on v0, v1 through v6 and got back v0 star through v6 star. Let's suppose, as before, that v2 star, v4 star, and v5 star are 0 vectors. So consider how orthogonalize would run. In its third iteration, it takes v3 and projects it orthogonal to the vectors v0 star, v1 star, and v2 star to compute v3 star. Well, how does it do that? It subtracts the projection of v3 along v0 star. Then it subtracts the projection along v1 star. Then it subtracts the projection along v2 star. But since v2 star is 0, the projection is the 0 vector, so subtracting does nothing. So the result is the same as if the algorithm had projected v3 orthogonal to v0 star and v1 star. v2 star played no role. 0 starred vectors in the second argument of project orthogonal are ignored. So if we ran orthogonalize on just the vectors v0, v1, v3, and v6, the output would be exactly those vectors v0 star, v1 star, v3 star, and v6 star as we got here. We already know that those vectors, v0 star, v1 star, v3 star, and v6 star, form a basis for the vector space that's the span of v0 through v6. And we've seen that v0, v1, v3, and v6 span the same space. They have the same cardinality, so they also form a basis for that vector space. Here's another way to see that our procedure is correct. Recall that we had a matrix equation relating the original vectors to the starred vectors. The matrix whose columns are the original vectors equals the matrix whose columns are the starred vectors times this invertible triangular matrix. Now, suppose we run find subset basis on the vectors v0 through v6. Let big V be the span of those vectors. Here's the matrix equation in which we write those vectors in terms of the starred versions times the invertible upper triangular matrix. And let's suppose, as before, that v0 star, v4 star, and v5 star are 0 vectors. So let's delete those vectors. So this is 0, this is 0, and this is 0. So we're going to delete those columns from this matrix and delete the corresponding rows from the triangular matrix. And we get this. Thus, the span of v0 through v6 is a subset of the span of v0 star, v1 star, v3 star, and v6 star. So that shows that these starred vectors form a basis for big V. Now let's delete the original columns corresponding to the 0 vectors, v2, v4, and v5. And delete the corresponding columns of this matrix. And we get this relationship. Now, this triangular matrix is invertible. So we can move it to the other side, multiplying by the inverse. And we get this relationship. Now, this shows that v0 star, v1 star, v3 star, and v6 star can all be written as linear combinations of v0, v1, v3, and v6. So that shows that these remaining starred vectors are in the span of the remaining unstarred vectors. So that shows that the remaining unstarred vectors, v0, v1, v3, and v6, are a basis for big V. Now, in principle, we said this algorithm finds a basis for the space spanned by v1 through vn. We use orthogonalize to compute v1 star through vn star, and then return the list consisting just of the non-zero vectors. However, the computer uses floating point numbers. And due to round-off error, vectors that are supposed to be 0 won't end up being exactly 0. So instead, we'll modify the algorithm to consider a vector to be effectively 0 if its norm squared, that is the dot product of v with itself, is very small, say less than 10 to the minus 20. So here's the revised algorithm. It applies orthogonalize, and then it returns the list consisting just of those vectors whose squared norms are greater than, say, 10 to the minus 20. Now, this procedure, which finds a basis for the space spanned by v1 through vn, can in turn be used to define the rank procedure and the is-independent procedure. And we can use the same ideas in find subset basis as well.